Welcome back to Calculus 2, Section 5.5, Alternating Series. In the previous two videos, we've made good progress on our journey of convergence tests for infinite series. We've had the divergence test, the integral test, two comparison tests, the comparison test and the limit comparison test. All four of those series had sequences which are of positive terms. Here in this video, we're going to look at a sequence which alternates. Our notation is going to be, instead of the ANs being non-negative, we'll let BNs denote the non-negative portion. And then for the ANs, we'll set AN to be -1 to the n times BN. Alternatively, AN will be -1 to the n plus 1 times BN. On the AN on the left here, with n equaling 1, you would start with a negative term, and then positive, back to negative, and so forth. Versus on the right, the AN begins with a positive term, then goes negative, back to positive, back to negative, and so forth. These are alternating. And if you have a series such that the AN is -1 to the n times BN, where BNs are non-negative, or AN is -1 to the n plus 1 times BN, then that series is an alternating series. Okay, so this is a definition of an alternating series, what it means to be an alternating series. Let's look at an example. We first introduced the harmonic many videos back. The harmonic is summing up 1 over n's. If we take the 1 over n's and we have them alternate, beginning with positive, then negative, then positive, then negative, that is termed the alternating harmonic series. All right, so this is going to serve as a good example to investigate alternating series. And as the previous two videos introduced some convergence tests, one main objective of this video is to introduce an alternating series test to test convergence of a series. So for example, the alternating harmonic series is an alternating series. Let's investigate its behavior to determine the convergence of it. Recall that if we sum up 1 over n's, that defines a p series with p equaling 1, and as such, it diverges. So does the alternating terms lead to a convergent series? So that's reminiscent of telescoping series, which we saw a few videos back. And the idea there was that if you add something in and then subtract away, that the cancellation helps the series converge. Okay. So here we have the alternating series, the alternating harmonic series, and then the first few terms written out. Now, we can pair the first term and the second term, pair the third term and the fourth term, and so forth. In doing so, we can observe that each pairing is looking at a difference of two terms, and it's always a large term minus a small term. As such, each of these pairings is going to produce a positive difference. Now, like before, when you want to investigate the convergence of a series, you consider the convergence of partial sums. Here, we're going to take a slightly different tact in that we're going to consider the sequence of odd indexed partial sums on one hand, and on a second hand, the sequence of even indexed partial sums. Let's start with the odd indexed partial sums. Let the odd index be represented by 2 times k, integer k, plus 1. Using our pairing method, we'll come up with k pairs. Each of those k pairs is a positive quantity. And then add in the last 2k plus first term to come up with the entirety of the 2k plus first partial sum. All right. As we want to consider the sequence of odd indexed partial sums, if we peel off the last 2 terms being added in and consider the sum of the first 2k minus 1 terms, then we would have the partial summation with index 2k minus 1. Okay. To recover back the next odd indexed partial sum, we would add back in the 2 terms we subtracted. Now, as we noted earlier, each odd indexed partial sum is a positive quantity, yet this quantity that we add in to the previous odd indexed partial sum, that this quantity is now a large quantity with a minus on it, plus a small quantity as a positive term. Therefore, this difference is less than 0. It's negative. What does that mean? That means that as we're taking odd indexed partial sum and moving to the next odd indexed partial sum, we're decreasing. Okay. Nice. So we have a decreasing sequence if we consider odd indexed partial sums. Let's write that down. Take the sequence of odd indexed partial sums. We've shown that 1, it's monotone, decreasing, as we're always adding in a positive quantity to begin with, and it's decreasing, therefore it's going to be bounded above, and then it's also bounded below, since these k pairings are all positive, and the last term that we add in is positive. So the sequence is both monotone decreasing and, through this observation, is also bounded. Very nice. Well, that gives us good information. It puts in our hand the notion that the odd indexed partial sums converge. They converge by the monotone convergence theorem. Now, we can repeat similar arguments applied to the even indexed partial sums and also get convergence of that sequence of terms. We're going to leave it to you to work out the details. One difference is that for the odd indexed partial sums, they are a decreasing sequence. Here, you should find that you obtain an increasing sequence. Good. Let's continue. So we have established that the odd indexed partial sums converge, that the even index partial sums also converge. Okay. The question then remains, do these two sequences converge to the same thing? So they don't necessarily have to. We're going to show that they actually do. Okay, how can we do that? We know that they both converge. Pick one. Let's pick the odd indexed partial sums. Suppose that they converge to a quantity S. Well, we know how to rewrite an odd indexed partial sum in terms of an even indexed partial sum, we would take the even indexed partial sum and then add in the next term. So that's how we can rewrite this guy. And then by properties of limits, we can distribute the limits. Well, a nice thing happens to this 1 over 2k plus 1. It limits out to 0. And because it limits out to 0, we get that the limit of the odd indexed terms equals the limit of the even indexed terms. Nice. Well, what is all this showing? This is showing that the sequence of partial sums converges to some quantity, and therefore the alternating harmonic series converges to a quantity S. Now, on a separate sheet of paper, title that sheet of paper goal, and put down as a goal, we're not going to accomplish it in this video, but in a future video, you will accomplish the goal of showing that the alternating harmonic series actually takes a value, ln of 2. We need to develop some further machinery to achieve that goal, but let's put it down on a sheet of paper as something to look forward to. Okay, nice. Let's continue. So we've shown that the alternating harmonic series converges. Recall that removing the alternating portion of the series results in the harmonic series, which we know diverges. So this is a curious situation that throwing in the alternating part really helped out, and it led to convergence of the series. Very good. Nice. All right. This picture here is depicting the arguments we used to establish convergence. Okay. So draw a sketch like this. We've got an x-axis. We have a vertical line. That vertical line actually occurs at ln of 2. And then we have some horizontal line segments which are either in blue and then alternate to red, back to blue, alternate to red. And then we have some red dots to the right of the vertical line, and we have some blue dots. Okay, let's try and make sense of this. The first red dot occurs at x value 1, and that's because the horizontal line segment in blue represents the first term 1 in the alternating harmonic. Therefore, the red dot is going to be the first partial sum. Now, in the alternating harmonic series, after 1 is -1/2, so the red horizontal line segment represents the second term. Adding in the second term to the first partial sum gives the second partial sum. And then we repeat. Add in a third to get S3, add in -1/4 to get S4, and so forth. And what you can observe is, as we've shown analytically, that the sequence of odd indexed partial sums decreases in value versus the even indexed partial sums will increase. And again, the green vertical line is the limiting sum, ln of 2. Okay, so let's zoom out a little bit. And here we're watching further and further terms being added in to give you a stronger visualization of the even indexed terms, asymptoting up to ln of 2, and the odd indexed terms, asymptotic from above to ln of 2. Nice. Okay, so we have gone back to the original picture where the vertical green line is now just denoted as an arbitrary S, that the first horizontal blue line is now indicated by just a B1, and the red horizontal line is indicated as negative B2. And for this nice picture to hold, what we want is for the sequence of BNs to be monotone decreasing, to get smaller and smaller. And then as they're smaller and smaller, that will result in even index increasing and odd index partial sums decreasing. And then for them to be asymptotic with some nice vertical line, x equals s, we'll need that the limit of those terms tends to 0. We have to have that the blue and consecutive red terms get closer and closer. How does that happen? That only happens if the BNs tend to 0. Nice. So again, this gives that the sequence of even index will converge to S, and the sequence of odd index partial sums converges to S. And this is the alternating series test. So to perform the alternating series test, we want to check that we have an alternating series, which means that we have a sequence of non-negative terms, Bn. You check 1, that that sequence is monotone decreasing, and then you check 2, that they limit to 0. Under such a situation, then either alternating series defined by these Bn's will converge. Good. This is AST. Do an example. All right. So we have a sequence of terms, an, which can be broken up into the alternating factor and then the Bn factor. You first want to identify the Bn's. So Bn would be 1 over n cubed. We need to check 2 conditions on the sequence of Bn's. We need to check 1, that they decrease. There are various ways to check that a sequence decreases. Here we're looking at a current term and then the next term. This is Bn and then Bn plus 1. And since n plus 1 is bigger than n plus 3, n plus 1 is bigger than n, we get that their reciprocals have the opposite relation. So second is that the Bn's will limit to 0. These are the 2 conditions required by AST. They're both satisfied. So we conclude that the given alternating series converges, and the method by which we verified is AST. Beautiful. Note that if we were to sum up just the Bn's, we would have a P series with P equaling 3. What do we know about a P series with P equaling 3? 3 is strictly bigger than 1, hence it converges. And then the alternating P series with P equaling 3, the alternating portion just helps it converge that much faster. Let's look at an example. Here we have an alternating series. Isolate out the Bn's as ln of n over n. Note that we've already done the case of 1 over n as Bn. Thus, introducing ln of n into the numerator makes the Bn's converge to 0 slower. Let's take a look, run through the alternating series test. We need to do 2 checks. We need to check 1, that the sequence is monotone decreasing, and 2, that it converges to 0. Let's do that. The checks of establishing monotone decreasing can be done in various ways. Here's a second way. Identify the bn's as a function evaluated at integer inputs, and that allows you to then differentiate the f. If you find that the derivative of f is negative, then the function is decreasing, and thus the sequence is decreasing. Nice. The second one, in taking a limit, you'll want to employ L'Hopital's. Derivative of the top gives you 1 over n. Derivative of the bottom gives you 1. 1 over n goes to 0. Very good. So by AST, we're able to conclude that this given series converges. Beautiful. Here's one for you to try. Use the alternating series test to determine the convergence of the given series. Fantastic. Now, in looking at convergence, to make it useful in an engineering sense, is to determine the error. Let's look at the error in approximating an alternating series. Okay, well, go back to the basics. An alternating series, what is it? We can break up the terms of an alternating series as an alternating portion and a non-negative portion. And that we've looked at this notion of when we have the bn's monotone decreasing and limiting to 0, we'll get that the even indexed partial sums converge, as well as the odd indexed partial sums converge to the same value. All right. Now, here in the zoomed in picture, we have B2 highlighted. That's the difference between S1 and S2. Here's B3, the difference between S2 and S3. B4 is the difference between S3 and S4. And more generally, Bn plus 1 is the difference between S sub n and Sn plus 1. So this next term, if you look at the nth partial sum, the next term is the difference between the current partial sum and the next partial sum. But that the difference between the nth partial sum and the true limit is going to be a smaller quantity than the next term. And that nth partial sum difference with the true limit is exactly the remainder. Nice. So we can state that out in a theorem that for an alternating series, the estimate on the remainder is rather straightforward. You simply look at the next term. Now, we need absolutes on the remainder because the remainder could be positive or negative. And we know that the next term, Bn plus 1, is a positive quantity. Good. So this is giving an estimate for the remainder. Very nice. Do an example. Let's go back to our convergent alternating series where the bn's are ln of n over n. And then let's approximate the 20th remainder. Well, from our theorem, we can approximate the 20th remainder by letting n equal 21 in Bn. And then plugging this into a calculator, we can come up with approximately 0.145. Very nice. Your turn. Here, you are asked to do two things. To first verify that the series converges. And then after verifying that the series converges, estimate the 20th remainder. And again, note that if we were to swap out the ln with a 1 and ignore the alternating portion, what we'd be left with is a p series with p equaling 0.1. 0.1 is clearly less than 1, and that series would diverge on its own. All right. So we've had the definition of an alternating series. We've looked at the alternating series test, and we've seen that there is a simple estimate to the remainder of an alternating series. Okay, now we're going to switch gears slightly. We're going to talk about different types of convergence called absolute and conditional convergence. A model for that is the harmonic series. Remember, the harmonic series is a p series with p equaling 1 that it itself diverges. But if we have the harmonic alternate, that alternating helps the series to converge. If we compare that with a p series where p is bigger than 1, then that series is already convergent, and by alternating terms, that's only going to help it converge. So, in looking at the right-hand sides, looking at the alternating harmonic series as a convergent series versus the p series as an alternating p series being convergent, these two convergents seem to be of different strength. That the convergence on the p series, p greater than 1, seems to be stronger than the convergence on the p series where p is less than or equal to 1. So that leads to a definition where the strong convergence is absolute convergence. If we have a series that converges even without it alternating, then the series is absolutely convergent. On the other hand, if you have a series that does converge, but it only converges on the condition that you do not throw away the fact that it alternates, then that series is conditionally convergent. All right, so there are grades of convergence. And we'll term these as AC and CC. AC for absolutely convergent and CC for conditionally convergent. Let's go back and look at our motivating examples. The alternating harmonic series is conditionally convergent. Why? If we throw absolutes on the ANs, we end up with a harmonic series which diverges. Thus, the given alternating harmonic series converges conditionally. On the other hand, for the alternating p series, p equaling 2, we know that it converges. But in fact, if we put absolutes on the terms, that we're still left with a series that converges. Thus, this alternating series is absolutely convergent. All right. So absolute versus conditional is looking at whether the convergence is strong or weak. Strong in the case of absolute convergence and weak in the case of conditional convergence. Nice. So, this theorem is saying that absolute convergence implies convergence. Let's take a look at a proof. In the proof, we need to start with an assumption. Let's start with assuming we have a series that converges absolutely. If we look at the ANs without absolutes on them, the AN is either non-negative or the AN is negative valued. Okay, how can we use that to our advantage? Well, if we add together the AN with its absolute, if the AN is negative valued, then that sum will be 0. On the other hand, if that AN is non-negative, then adding it with its absolute will double up on that value. Nice. So we can start with a sequence, make an assumption that it is defining an absolutely convergent series, produce a new sequence, and note that these terms are always controlled by terms from a sequence defining a convergent series. This is exactly the comparison test to say that if we were to add up the sequence of absolute AN plus AN by being controlled by a convergent series, that it itself converges. Very good. We're almost done. What are we trying to establish? We want to show that the series converges. If we look at the series, it's the sum of the ANs. To each AN, add 0, you'll still have AN. Add to AN 0 in the form of the absolute of AN minus the absolute of AN. And then distribute the summation thanks to algebraic properties of convergent series. And then we have that our series may be viewed as the same thing as the difference of this quantity and that quantity. In other words, our series is a finite value. And we are done. Very good. Okay, so let's do an example where we look at a series and we determine what type of convergence do we have. Is the convergence absolute? Is the convergence conditional? Or is there no convergence at all? So, presented with this series, we can note that it is a alternating series. So let's try the alternating series test. To employ the alternating series test, we want to break off the non-negative portion, Bn. Then the Bn needs to satisfy two conditions. It needs to be monotone decreasing, and the Bn's need to converge to 0. Both of these conditions are met. Hence, the series converges by AST. All right. Well, what we've done is we've established that the given series is a convergent series. Therefore, we can scratch off the case of no convergence. We're now left with deciding, is the convergence absolute or is the convergence conditional? Okay, so that means that we need to remove the alternating portion and ascertain whether we still have a convergent series. And we do not, since putting absolutes on the ANs results in trying to sum up the BNs, but the BNs are essentially a P series with P equaling 1/2. Now, there is a shifting of terms. So if we start our index instead of at 1, if we start from 3, then we'll have the second remainder on a P series where P is equal to 1/2, and this is not a finite value. Thus, while the given series does converge, it is absolutely divergent, or in other words, it is conditionally convergent. So the series converges, but the sum of the absolutes diverges. Thus, the series is only conditionally convergent. Very good. All right, so here are some examples for you to play around with. You have three choices: AC, CC, or diverges. Very good. And then here are some challenge problems. Same situation. Do the given series diverge, converge conditionally, or converge absolutely? Excellent. So that is absolute versus conditional convergence. We now want to look at the Riemann rearrangement theorem. All right. So we're going to do an example here. And the point of the example is to exhibit how infinity is rather bizarre. That assumptions that you make based on finite observations cannot blindly be translated over to infinity. Okay. So what do we mean by that? Well, we're going to do a rearrangement, and we're going to come up with a result which is rather bizarre. All right, what do we mean? Let's start with the alternating harmonic series. So that's here on the left-hand side, and then using this form, write out the first few terms, and then take it on faith. Remember, this is our goal, that later on we'll establish the actual value is ln of 2. Okay, we're going to need some notation. So we're going to let the alternating harmonic be given as the sum of ANs, where ANs are -1 raised to the n plus 1 over n. Okay, so the ANs correspond with the alternating harmonic. Good. Let's play around. We can use properties of convergent series. We can multiply through by 1/2 in a natural way. We can multiply 1/2 on the alternating harmonic series. That means that we're going to get 1/2 of ln of 2. But the properties of convergent series allow us to push the 1/2 onto each term. Half of 1 is a half, half of -1/2 is -1/4, and so forth. So far, so good. Play around a little more. Let's interject zeros in front of each term. And then now let's use this to define a new series given by bn's, where all of the odd indexed terms are 0, and then the even indexed terms with index 2n are an divided by 2. All right. So we want to add up the series given by ANs with the series given by BNs. That means we should come up with a value of ln of 2 summed with 1/2 ln of 2. So writing that out, thanks to properties of convergent series, if we take the ANs and the BNs, put them together to form a new series, that the value produced will be the sum of their respective sums, which is 3/2 times ln of 2. All right, no controversy here. Everything is handy-dandy. Let's investigate this summation of the ANs plus summation of the BNs. So on the first row, we have the summation of the ANs, the alternating harmonic series. On the second row, we have the summation of the BNs, which is 1/2 the first row, where we interject zeros before each term. Okay, and then let's go and sum ANs with BNs. So when n is equal to 1, we get 1 plus 0, or 1. Move on to the n equal 2 case, we get a cancellation. Move on to the n equal 3 case, we produce 1/3. On to the n equal 4 case, we get -1/2. The n equal 5 case, we get 1/5. N equals 6 case, we're going to get another cancellation. N equals 7 case, we'll bring down a 1/7. N equal 8 case, we'll get 1/4 in the negative. And then continue on and on. And that will be equal, on the right-hand side, ln of 2 plus 1/2 ln of 2. All right, great. However, if we look at the left-hand side and we notice that we're reproducing all of the original terms from the alternating harmonic series, but in a different order, and if we put them back into the original order, we'll have ln of 2, which is not 3/2 ln of 2. So by this rearrangement, we're able to take the original terms, use just the original terms, and produce a completely different value. Using only finite terms, that will never happen. Thus, infinity is bizarre. And the reason why this is occurring is because of the conditional convergence. So that conditional convergence is great, but it has a bit of a weakness. There's an Achilles heel to it. You cannot willy-nilly rearrange terms and produce the same value. All right, so absolute convergence is king. Nice. So here's a fun challenge problem. We're looking at a video of a Desmos output. And we have a bunch of dots being plotted in the plane. We have a horizontal line in green, 2 of them. We have the x-axis. We have purple dots, orange dots, red circles, blue circles, and black x's. So this is the first 10 terms in various sequences. Let's look at the first 100 or so terms in these sequences. So the purple dots are converging to some value given by the green horizontal line. The orange dots likewise converge to a separate value given by the second green horizontal line. And then the red dots, blue dots, and black x's are all asymptotic to 0. Okay. So these quantities correspond with the alternating harmonic series and the rearrangement example that we just did. So your challenge is to reproduce this graph where the ANs are the alternating -1 to the n plus 1 over n. The BNs are you multiply the ANs by 1/2 and then interject zeros. And then the black x's are the sum of the ANs and the BNs. Then the orange dots are the sum of the ANs. And the purple dots are the sum of the AN plus BNs, where the orange dots limit out to ln of 2 and the purple dots limit out to 3/2 ln of 2. Nice. So have fun there. And that brings us to the end of this video. Thank you so much for watching. Please like if you find the video useful. And I will see you on the next one.